Today on How It's Made. Dial thermometers. Hummus. Spent fuel containers. And straw sombreros. In the world of temperature gauging, the dial thermometer is a lot easier to read than a glass stem thermometer. A needle points to bold numbers on a dial, and even from a distance, it only takes a quick glance to confirm an initial impression that things are heating up. All the highs and lows are plain to see on the face of a dial thermometer. It often comes with lengthy tubing to measure temperature from afar. It's a handy feature for power plants and heating and refrigeration systems. To begin, rollers straighten very narrow metal tubing. Then a blade cuts it to length depending on the application. As the blade makes the cut, a mechanism pries open the ends. Next, a worker inserts a fitting into a much wider tube that will become the thermometer sensor bulb. He secures the tube in a fixture and welds the narrow tubing machined earlier to the fitting on the end of the bulb. With the bulb and tubing now linked, production moves to the next stage, the making of the burden tube, which is a kind of a spring. A worker cuts flat wafer-thin tubing to length. Down the line, they clamp the flat tubes in a device that's on a track. It moves past an arc welder that melts and closes one end of the flat tubes. Here's a before and after comparison. A worker now encloses the tube in a die and drives a pin into its open end. This widens and redefines the opening from inside and outside. He slides it over another pin and activates a mechanical punch press. This fine-tunes the shape and dimensions of the opening. The next worker clamps the tube in another device. He operates a roller to wrap it around a mandrel, bending it into a C shape. This completes the thermometer's burden tube spring. The next worker clamps a bracket to the bottom of the burden tube. He inserts a small piece of connector tubing in the burden tube hole and applies liberal amounts of a flux compound. The flux prevents tarnishing of the metal as he melts silver solder to braze the parts together and to seal the opening. Now a test. He pumps gas into several burden tubes and immerses them in water. If no gas bubbles out of the tubes, it means the tubes are perfectly sealed. The gas pressure also causes the tubes to spring into action. It's this action that will move the pointer on the dial of the thermometer. The next worker attaches a brass connector to the tubing. He brazes them together to create a solid bond. He folds the brazed parts into the curve of the burden tube and pushes it into place with a mechanical press. He installs the gear assembly that will translate the linear movement of the burden tube into the rotational movement of the thermometer pointer. He screws the dual temperature dial to the burden tube assembly. The more detailed and extensive the scale, the bigger the dial. This one is mid-sized. And now everything comes together as he tethers the sensing bulb along with a short fill tube to the back of the burden tube assembly. Using a brazing torch and solder, he seals the connection. He then steam cleans the brazed joint. He buries the bulb in a hot sand bath that causes any moisture in it to evaporate. Through the fill tube, he fills the bulb with nitrogen gas. To calibrate the thermometer, he plunges the sensing bulb in boiling water and adjusts the pressure of the nitrogen gas until the dial reads 212 degrees Fahrenheit. The fill tube's job is now done, so he crimps it to seal it off. He tests its accuracy by immersing the sensing bulb in numerous controlled baths, each one a different temperature. And if it's on the mark, he encloses the inner workings in the stainless steel case. He protects the joint with a special metal spring and snaps a clear window to the case. A gasket between them ensures a dust-proof seal. He screws a part called a well to the sensing bulb connector. The well will protect it in high-pressure situations. And this dial thermometer is now ready for the ups and downs of temperature gauging. Hummus is the original snack food. People have been eating this chickpea dip for thousands of years. Countries from the Mediterranean to the Middle East lay claim to its invention. But one thing is beyond dispute. As an appetizer or side dish, hummus has real staying power. Hummus is a vegetarian form of protein, which could be why more and more people are choosing to take a dip. The word hummus is actually Arabic for chickpea, which is of course the main ingredient. The chickpeas arrive at the factory in dried form. They ride a conveyor upward and then spill down onto a long vibrating tray. It shakes out heavier contaminants like pebbles or twigs. The contaminants fall into a bin below, while the chickpeas bounce off the tray and into a tub of filtered water to be rinsed. Still dripping wet, it's onto a conveyor with perforated buckets. The water drains from the chickpeas as they're transferred to big tanks. Each tank holds thousands of little chickpeas. They add clean water and soak the chickpeas. After 14 hours in the tank, they swell to twice their size and soften up. They pump the softened chickpeas into big trays, which they stack on a cart. Then it's into a huge cylindrical steam cooker that's been preheated to around 255 degrees Fahrenheit. They bake the chickpeas for just over half an hour. This softens them even more and darkens the color. From dried beans to soaked and then cooked. They now transfer the cooked chickpeas to the next conveyor, and they're on their way to being ground to a pulp. This is the grinder, now being reassembled after cleaning. It has two sharp-toothed circular blades. One is stationary and the other revolves. A big turn screw will force the chickpeas through these toothed blades to grind them up. A quick test confirms this grinder is in working order. Meanwhile, the chickpeas have arrived at a hopper above the grinder. As the chickpeas spill into the hopper, they add water and a blend of sunflower and olive oil, followed by salt, garlic, and other dry ingredients. The chickpeas and other ingredients flow into the grinding device below and are turned into a paste. The next ingredient is tahini. It's a thick paste made from ground sesame seeds. 3 powerful pumps pulverize the tahini to evenly disperse the particles, so it can now be blended with the chickpea mix. Big steel blades revolve to thoroughly mix all the ingredients in a tank and produce hummus. For different flavored hummus, they add red pepper, more garlic, or other ingredients. After the blended product is pasteurized, a technician takes samples for lab testing, for mold, shelf life, and other tests. She also does her own taste test. If the flavor seems even slightly off, they'll put the product on hold and tweak the ingredients. But this batch gets the nod. Meanwhile, plastic containers are queuing for a fill-up. Machinery moves them forward toward piston fillers. The pistons push the creamy hummus out of nozzles and into the tubs. Now, filled to the brim with hummus, the tubs travel under a sheet of plastic film. Hot round irons melt the plastic to seal it to the rims. Suctioning devices swoop down to apply the lids, and the hummus heads towards a roll of adhesive-backed labels. A sensor detects the approach of the tubs and triggers a device with little air jets to slap the labels on the lids. This hummus production has gone very smoothly indeed. Spent fuel containers are designed to take the heat, the kind caused by the most radioactive of waste, used nuclear fuel. These fuel rods are too dangerous to be casually disposed of, but encased in special spent fuel canisters, the risk should be contained. Nuclear waste sits in a holding pattern, and that means storing it in massive cylinders until there's a way to dispose of it. These containers start with a big rectangular sheet of stainless steel. A special circular cutter carves a beveled edge onto it. They feed it to rollers which curl the sheet into a cylinder. It takes 4 trips through the rollers to really round it out. They tuck a template inside the curve to check the radius. Next, a welder joins the neatly beveled edges to complete the cylinder. This cylinder will be the outer wall of a canister. The canister will fit inside a big cylinder called an overpack. Its outer shell is just under an inch thick, about the diameter of a quarter. As you can see, building a container to hold used nuclear fuel is a many-layered process. The next step involves the lid, made of multiple steel discs with concrete placed between the steel layers like a sandwich. Incredibly, high-pressure water jets easily cut through the thick steel to produce the discs. A computerized tool cuts a grooved profile along the edge of each disc. They also machine the top of each disc to the correct profile, and then measure to confirm it's exactly right. Next, a computerized laser slices through more stainless steel plating to produce long, narrow panels. Each is designed to fit together to create a grid of storage cells inside the canister. They line each panel with an aluminum alloy that's neutron absorbent, and they place a piece of steel sheathing on top of that. They weld the steel sheathing to the steel panel, encasing the neutron absorbent material. Working within a metal framework for guidance, they weld 4 of the lined steel panels together to create a fuel cell grid for one used nuclear fuel bundle. They then build a 68-cell grid. With that complete, they're ready to piece together all the parts of the spent fuel canister. They first lower the inner shell onto the base plate. The shell is held steady by a supportive structure as they weld it together at the seams. Moving inside, they install numerous bars to support the fuel cell grid. With the canister now wrapped in plastic to keep it clean, an automated cutter gradually shaves down the rim to trim it to the correct height. Precision is everything. Using a level and a laser, they ensure that the trim job is even and exact. Once they're satisfied, a crane carries the fuel cell assembly over to the canister and then suspends it above the open cavity. It dangles briefly as workers inspect the assembly. They give it the thumbs up, and the crane then lowers the fuel assembly into the cylinder. It's a snug fit, with about 4/10 of an inch of clearance between the inner assembly and the wall of the cylinder. This technician inserts a camera into each cell of the grid and scrutinizes the image. He's looking for any debris, that could hamper the installation of the nuclear fuel bundles. Both the cylinder and the fuel cells have been meticulously cleaned, but the camera inspection confirms they haven't missed anything. So it's time to put a lid on this nuclear waste canister. It's a trial fit. The lid will be permanently welded to the canister later, once the used fuel rods are safely inside. The canister will then be placed inside the overpack, with concrete poured between the walls. That should keep the hazards of nuclear waste entombed indefinitely. The word sombrero is derived from the Spanish sombra, which means shade. The expansive brim of these Mexican hats is designed to cast a wide shadow over the face, neck, and shoulders. Fancier sombreros are made of felt. Regular ones are woven out of straw. This workshop makes traditional straw sombreros in many styles. This model's called a Winston. This one, an Americano. Here's the Speedy, after the cartoon mouse Speedy Gonzales. And the Cassidy. These sombreros are handcrafted. The straw is white palm leaves purchased from a supplier in the region. First, workers soak a bunch in water for a minute or so to soften them up. Then, using a needle, they tear strips about 2/10 of an inch wide. Then, they take 3 strips at a time and braid them together into a single strand. They intertwine several braided strands, making a long braided straw rope. Then they feed this rope into a manually operated press. The press flattens the rope until it's just about 4/100ths of an inch thick. This flattening makes the coarse rope soft enough to sew. With the raw material prep work done, hat construction can begin. They take the rope and wind it in concentric circles, sewing one circle to the next. They first make a flat base, then turn the base on its side and keep sewing until they form the cup, the part of the sombrero that sits on the head. They place the cup over a form to check the size. Then they resume sewing on more straw rope, working outward now to form the hat's brim. Brim width varies by style. They measure to make sure it's the correct size. Once the sombrero is finished, they boil water. Pour in gelatin. Stir until it's completely dissolved. Then soak the hat for about a minute. The gelatin penetrates the straw fibers. Then they hang the sombrero out to dry in the sun for about 3 hours. The workshop has a steel mold for each sombrero style it produces. Workers place the sombrero on the appropriate one in a hot press, then close the press for 3 minutes. The heat and pressure combined form the straw to the mold shape. The heat also hardens the gelatin, locking in the shape permanently. Many sombreros have a decorative band encircling the base of the cup. This band, called a scarf, is handcrafted, typically out of leather, or like this one, out of maguey, a fiber from the stalk of a tropical plant native to Mexico. A few dabs of glue hold the scarf in place. Once a sombrero is finished, the workshop tags it with a certificate stating the model and serial number. Sombrero shapes can vary significantly, but they all share a common characteristic, a wide brim to protect from the blazing sun. Certain models have an extra feature, a cord or leather drawstring, so the hat doesn't fly away in windy weather.